Hello. This lecture will be on free fall and non-free fall for chapter 4. This corresponds with the two handouts for your notebook, number 31 and 32. So Newton's second law of motion, F force equals mass times acceleration. Free fall. So we talked about free fall in the previous chapter as well. Basically, free fall is falling under the acceleration of gravity with no air resistance, so no friction. And um, there's this slide here is just showing us how even though two objects may have a different force of gravity, they'll still have the same acceleration. And this comes from manipulating the equation for Newton's second law. So F equals m times a. Forces also weight is a way of describing that. And g is the acceleration. So F equals m times a can be rearranged as F over m equals a. And in this case, this acceleration particularly will be gravity. So if you have a mass that is twice as large as another mass, then the force of gravity on that, the force of gravity on that object will be twice as well. And then when you solve for g, gravity, it actually cancels out. So they have the same acceleration regardless of mass. Now, this is, of course, in free fall, which is without air resistance. So anytime objects are falling without air resistance or they're falling in free fall, all objects will fall with the same acceleration of 10 meters per second squared. So 10 meters per second per second. Now, more precisely, that's 9.8, but we're using 10 just to make the calculations easier to estimate. All right. First practice question. At one instant, an object in free fall has a speed of 40 meters per second. 1 second later is. So the key information we need from this is that it is in free fall. We know that it's currently at a speed of 40. And we know that all objects in free fall change their velocity by 10 meters per second every second. So 1 second later, the object should be falling at 50 meters per second, making the correct answer C. Here's an additional explanation with built in. So if you need a chance, wait a minute. So this is, what is this? Okay, I had to read that more carefully. When I skimmed it, I misread it. So it's just saying that if we're assuming that the object is falling downward, and so its velocity is changing by 10. So in other words, it's increasing by 10. If it was traveling upward, it would still technically be in free fall, but the velocity would change to 30 meters per second in a second. But we're assuming here that the object is falling downward. Also, 30 isn't an option, so that kind of narrows it down as well. All right, next question. A 5 kilogram iron ball and a 10 kilogram iron ball are dropped from rest. For negligible air resistance, the acceleration of the heavier ball will be. So negligible means ignoring it. So we're ignoring air resistance. So air resistance doesn't exist, which means we are in free fall. Also, the title of the question says free fall. So that's your tip off that there's no air resistance. So everything has the same acceleration, which is gravity. So it's the acceleration of the heavier ball will be the same as the 5 kilogram iron ball because we have no air resistance in this situation. Next question. A 5 kilogram iron ball and a 10 kilogram iron ball are dropped from rest. When the free falling 5 kilogram ball reaches a speed of 10 meters per second, the speed of the free falling 10 kilogram ball is. So to determine this answer, we need to know, are we in free fall or are we in non-free fall? When we're in free fall, we have no air resistance. So everything changes by 10 meters per second, and it doesn't matter what size it is or the mass of it. So these are both dropped from rest. So they both dropped like this, dropped. And then it says the 5 kilogram ball reaches 10 meters per second, which would occur in 1 second. And how fast would the other one be going? It would be going exactly the same. So B, 10 meters per second, because all objects fall at the same rate when there's no air resistance. Another description of that condition would be in a vacuum. In a vacuum, we have gravity, but we have no air resistance. All right, so that's the end of the first handout. The second handout is non-free fall. And we'll be just talking about the distinctions there. So we're essentially introducing friction here. Friction being the opposing force to gravity. So when an object falls downward through air, it experiences the force of gravity pulling it downward and air drag force acting upward. We also call this air resistance. And that is represented with the letter R here. Okay. So force of gravity is pulling it downward. We will refer to this often as weight. So I'm going to just put W. And then when downward, we have the action of air resistance, which I'm going to write as an R. So mg is mass times gravity, which is another way of saying weight. So m times g equals weight, which is a force. Another way of writing weight is actually F sub W. So that makes it more clear that it is a force, but specifically the force of gravity, which is the weight of the object. All right, air drag force acting upward, we're representing that with an R. When these two are equal, we're at terminal velocity, and we are no longer accelerating. So we start off with this rock right here, and it has that weight, right? It has that weight arrow downward. And when velocity is 0, and this is what you're writing in your notes, when velocity is 0, we have the weight of gravity acting on the object, but we don't have air resistance. Then as it starts to fall, pretend like these are all uniform and pointing down. It's kind of hard to draw with the mouse. Let me just draw all these first here. I need a couple more. One more. Okay, so this is 0 velocity. And then the last one, when the air resistance and the weight are equal, then velocity equals terminal velocity. In other words, it can't fall any faster than that because it's no longer accelerating. Acceleration requires a non-zero net force. And when air resistance is completely canceling out weight, that is a net force of 0. And when we are in the condition of net force of 0, acceleration has to be 0 as well. So if we have no acceleration, we have no change in velocity, thus it cannot go any faster. So as soon as the object falls fast enough to match the air resistance to the gravity, to the weight of gravity, then it doesn't speed up anymore unless it changes shape. So that's the exception. Like a parachuter would jump from an airplane, and then when they're ready to not smash into earth, they open their parachute, and that increases their surface area, which slows them down. But prior to that, their terminal velocity is faster than when they open the parachute. So assuming there's no change in shape or surface area, then this is a endpoint. There's no more changing of velocity. Now, when velocity is 0, we have no air resistance, so we have only weight downward. And then as velocity is equal to greater than 0, the air resistance starts to happen. Okay, so it increases. And then when it hits that point where it's equal to the weight of the object, the amount of air drag is equal to the weight of the object, then it no longer accelerates any further. Okay, so this would be a state of net force is 0, acceleration is therefore 0. All right, moving on to the next slide. The condition of non-free fall occurs when air resistance is negligible. Okay. When air resistance is non-negligible. So this is like a double negative because negligible means not, and then non-not. So what this is getting at is we have a situation of non-negligible. So we are not ignoring it. This means don't ignore. Okay, so this means don't ignore air resistance. Don't ignore. It depends on two things. So there's two things that affect how much air resistance something experiences. And the two things are speed and frontal surface area. So to give you an idea of how speed affects it, imagine your hand out the window of your car when you're going maybe 20 miles an hour. And then imagine sticking your hand out the window when you're on the freeway going 65 or 70. There's a significant difference in how much force you feel hitting your hand. So the faster you move, the more air particles you hit, and therefore the more force it exerts on you. So the faster something moves, the more air resistance it has, which that is the thing that leads to the buildup of air resistance leading to terminal velocity, right? So the faster and faster you fall, the more and more air resistance there is, leading to eventually no more increase in speed. The other factor that you can manipulate to change air resistance is frontal surface area. So what it means by frontal surface area is, so imagine here's the ground and I have a piece of paper and I drop it like this. It has a very small frontal surface area right here at the bottom of the piece of paper. If I drop the paper like this, then I have a large frontal surface area of the whole length of the paper there. So the frontal surface area is just the part that's going into the air. So falling downward, it would be the bottom surface area of the part facing the ground. If you've ever watched skydivers, they'll actually manipulate their body. So they'll lay flat like this with their arms spread and their legs out. And then if they want to like catch up to somebody, they'll go into this more of a dive position. And what that does is it just simply reduces their surface area, which therefore reduces their the amount of air resistant force that they're experiencing, allowing them to speed up a little bit. When they then return back to this kind of plank position, they'll slow back down, but they can temporarily increase their velocity by manipulating their body in the space, which is exactly what happens when they open their parachute. So they go from this person to all of a sudden they have all this surface area from their parachute that all the air is now hitting, which slows them down. It creates that air drag. Okay. All right. When an object is moving fast enough so that air resistance builds up to an equal force of gravity, you have then no net force, therefore no acceleration, and velocity does not change. Velocity is then constant when R equals weight. The sum of forces becomes zero, acceleration becomes zero. Your sub will show you the notes that go with this. There's a few things for you to write in, annotations for the slide. All right, here we have two definitions, terminal speed and terminal velocity. There is a distinction between speed and velocity, namely direction, right? Speed doesn't have a direction, velocity does. Often people use terminal speed and terminal velocity interchangeably, but there is that distinct difference that there is a direction implied. So terminal speed occurs when acceleration terminates, that means stops, when air resistance equals weight and net force is zero. Terminal velocity is the exact same thing. It's just that the direction is specifically identified in the question. So you just want to circle direction here and just highlight terminal speed and terminal velocity to show that you read that. All right, and then this is the last slide on the handout. And this is just kind of lays out the whole description of how a skydiver reaches terminal velocity. Remember that skydiving is done in non-free fall, meaning that there is air resistance. So a skydiver in fall after jumping from a plane, weight and air resistance act on the object. As the speed increases, the air resistance builds up, net force is reduced, and acceleration becomes less. When air resistance equals the diver's weight, net force is zero, acceleration terminates. Diver reaches terminal velocity, then continues to fall at a constant speed. And this is until that skydiver opens their parachute, which changes the dynamic and actually slows them down. A couple of questions. When a 20 Newton falling object encounters 5 Newtons of air resistance, its acceleration of fall is less than g, more than g, or terminated. So to decide what the answer is, so we know weight would be 20 downward, and they're telling us that the air resistance is 5. So the net force in this case would be 15 downward, would be the net force. Ooh, that does not look right. Okay, so downward is 20, upward is 5, net force is 15 down. That means it's still accelerating because there's a net force downward, but it's less than gravity because we know that it's there's already some air resistance happening, which means that the acceleration has already started to decrease a little bit. So it will be less than g. With that one. Okay. If a 50 Newton person is to fall at terminal speed, the air resistance needed is. So when we reach terminal speed, that's when the weight and air resistance are equal and opposite, meaning that the net force is 0. So if the person weighs 50 newtons, then that means that the air resistance would need to be exactly 50 newtons to counteract that, to give us a net force of 0. As a skydiver falls faster and faster through the air resistance. Okay, so the faster the person falls, the more and more air they hit. Therefore, the more and more air resistance they gain. Okay, so that would be increases. Next question. As a skydiver continues to fall faster and faster through the air, net force. So it's a little bit tricky here. So in this question up here, it said what happens to the air resistance. So as they're going faster, the air resistance is increasing, but their weight is staying the same. And this question asks us about the net force. So when the person is not moving yet, their net force is their weight downward. As they go faster and faster, the air resistance starts to cancel out some of that, and the net force decreases. So the faster the skydiver falls, the greater the air resistance and the lesser the net force, approaching 0. And then the acceleration. So the acceleration goes the same direction as net force. As the net force decreases, so does the acceleration. When the net force reaches 0, so does the acceleration. Consider a heavy and a light person jumping together with the same size parachutes from the same altitude. Who will reach the ground first? So if we were in free fall, they would land the same time because there's no air resistance. But we do have to take into account air resistance in this case. So since their parachutes are the same size, they'll experience the same surface area, which means that when they have the same velocity, they'll have the same air resistance. The difference here is that the heavy person has a larger weight arrow than the lighter person. Okay, so the lighter person has a smaller weight. But when, let's say, they're both going 10 meters per second, the smaller person will have this much air resistance and the heavier person will have the same amount. But notice that this one here has a net force of 0 now, but this one doesn't. So the lighter person will hit terminal velocity first, and the heavier person will keep accelerating. Because it has a greater terminal velocity, it will be moving faster, and as a result, get to the ground first. Okay, so free fall versus non-free fall. One more time. A coin and feather fall while air is present. The feather reaches terminal velocity very quickly because it has a large surface area and a small mass, and falls slowly at a constant speed, which is terminal velocity, reaching the bottom after the coin does. The coin falls very quickly, and air resistance doesn't build up to its weight over short falling distances, which is why the coin hits the bottom much sooner than the feather. Okay, so the question says, when the air is removed by a vacuum pump and the coin and feather activity is repeated, and you watched a video on this on Monday, the feather hits the bottom first, the coin hits the bottom first, or they drop together side by side. So when we're in a vacuum pump, that means we have no air resistance, which means we're in free fall. And when we're in free fall, all things fall together. There's no difference based on shape, size, or mass. Free fall versus non-free fall continued. A coin and feather fall in a vacuum. There's no air because it's a vacuum, so no air resistance. The coin and the feather will fall together. All right, so make sure you complete your annotations for both notes, handouts, and submit the Go Formative after answering all the questions. Thank you.